Hi, my name is Kelly Halloran, and today I'll be presenting a study on the loading of the equine third metacarpal during growth. We know that one of the leading causes of fatality in racehorses is fractures to the distal forelimb, which most commonly occur at the metacarpal phalangeal or MCP joint. Of these fractures during training, 23% are in the third metacarpal or MC3 bone. We also know that bone can be strengthened through mechanical loading during exercise and is most susceptible to change during growth. Therefore, if we can characterize the way that the MC3 develops during growth, we can work to create an exercise model designed to strengthen the bone and prevent potentially fatal injuries once the horses reach racing age. To characterize MC3 development, we took CT scans of the distal forelimb of 2 foals across 7 different time points, from 16 to 53 weeks of age, and then focused specifically on 7 locations across the MC3 bone. Our group has observed that foals spend a majority of the first year of their lives standing, where the MC3 is statically loaded vertically. So we modeled the bone as a beam, assuming an applied axial load of 30% body weight. Using hydroxyapatite phantoms we placed in the CT scans, we extracted bone density and used a previously established relationship to find the elastic modulus of the bone at each of the 7 locations. We began by plotting the bone area fraction, which is bone area divided by total area, and density across the whole bone for each time point. In general, as the foals aged, the diaphysis region experienced the most change, with the bone area fraction increasing and the bone density decreasing with age. This suggests that, while the bone is definitely growing larger, it is becoming less dense and generally weaker, with a lower modulus of elasticity. We then plotted the stress and strain at specific locations across the MC3 for every time point, normalizing by the weight of the foal. We found that the highest stress was at the diaphysis 2 location, while the highest strain was found at the distal 1 and proximal locations. This indicates that these locations may be more susceptible to fracture when the horses begin training. We also wanted to look at how the stress and strain change over time within the MC3. To do this, we looked at the slopes of the stress and strain plots. We plotted the change in bone area, or bone accrual, and the change in stress and change in strain for each of the 7 locations. We found that bone area accrual was highest in the distal region of the bone, while the largest increases in stress are found at the proximal end of the bone. Additionally, the highest increase in strain is found in the distal 2 location. While the exact mechanism of the adaptive response by bone to loading is unknown, this data could suggest that the bone is adapting more to stresses, as the highest bone growth area in the distal end is also the area with the lowest increases in stress. In fact, most of the fractures of the MC3 do originate from the distal end of the bone. One limitation of the study is that we assumed uniform cross-sections and didn't account for the density differences between trabecular and cortical bone. This could have slightly affected our calculated elastic modulus values, although they generally follow the same trends as previously published studies. Overall, we have found that there are certain areas of the MC3, specifically the proximal end, that are not adapting as well to increased stresses as the horse grows during its first year of life. If the stresses are increasing from static loading due to standing, we can expect even higher stress increases as the horse begins working at increased speeds, like walking and trotting, and the bones are subjected to muscle loading and joint movement. A better understanding of normal MC3 development will help us identify a time where the bone is most susceptible to an exercise intervention to strengthen it. In the future, we hope to continue this work by examining the stresses and strains on the MC3 during dynamic loading in vivo, such as walking and trotting, and eventually work to create an exercise model to reduce the risk of injuries in racehorses. I would like to thank the Mechanical Engineering Department at U of I, our funding sources, and my lab mates at the Tissue Biomechanics Laboratory for their help and support. Thank you for listening, and here are our references.